This lecture is intended as a supplement to an introductory lecture on basic MRI physics titled Spin Gymnastics. The reason for this supplement is because the introductory lecture led to several recurring questions regarding specific items that were only superficially covered or not covered at all in the introductory lecture, and because some people requested more quantitative information about some topics covered in that first introductory lecture. 7 topics will be addressed in this supplement. These being the field of view, the number of pixels in each direction in the image, the gradient strength and gradient duration, bandwidth, the sampling interval delta t, and k and delta k as they relate to k-space. We'll also look at the interrelationship between these factors. The topics of bandwidth and sampling interval will be addressed first, as will the relationship between these two. The MRI signal is received as an analog signal in the receiver coil. MRI analog signals have components at many frequencies. The highest frequency component in an analog signal determines the bandwidth of that signal. The higher the frequency, the greater the bandwidth. For analog to digital conversion, ADC, to result in a faithful reproduction of the signal, samples of the analog signal must be taken frequently. The time taken to measure each sample is the sampling interval, delta t. The number of samples per second is the sampling rate, or also called the sampling frequency. If the highest frequency component for a given analog signal is f sub max, the sampling rate must be at least twice f sub max. In other words, delta t is equal to 1 over 2 times the bandwidth. This is known as the Nyquist theorem, also known as the sampling theorem. If the sampling rate is less than twice the maximum frequency, some of the highest frequency components in the analog input signal will not be correctly represented in the digitized output. When the digital signal is converted back to analog, false frequency components appear that were not in the original analog signal. This undesirable condition is a form of distortion called aliasing. In MRI, sampling is in the complex mode, typically with 2 or more receiver coils. The MRI receivers collect both the real and imaginary data for each point, which enables distinguishing positive from negative frequency within the bandwidth. Thus, in MRI, delta t is 1 over the bandwidth because both the real and imaginary data is collected. This can be thought of as having to sample at twice the highest frequency of the MRI signal relative to the rotating frame of reference. For example, if the bandwidth is 32 kilohertz, the frequencies in the sampled signal range from minus 16 kilohertz to plus 16 kilohertz. In other words, the signal must be sampled at 2 times 16 kilohertz, which equals 32 kilohertz to avoid aliasing. That's 32,000 times per second. In MRI, the data that is coming from the body comes from different positions in the body. This is called the spatial domain or the position domain, and is received over a period of time, the time domain. So it's relatively complicated because at any point in time, the data is being received simultaneously from different points in space. And at any point in space, that point will contribute data at different points in time. Therefore, there are 2 types of frequency that need to be considered in MRI. One is temporal frequency and the other is spatial frequency. So temporal frequency usually refers to the number of cycles that something happens per unit time, typically per second. And spatial frequency refers to how many cycles of something happens over a unit of distance. So in this, you can think of this as waves on the ocean, or the wave that is drawn at the bottom right of the image, where one sees 5 waves over a distance of approximately 10 centimeters. So that would have a spatial frequency of 5 over 10 centimeters. Let's apply these ideas in an example of an MR image of the head, where we have a 24 centimeter field of view, and we decide we want to have 256 pixels across the field of view, which gives us a spatial resolution of a little bit better than 1 millimeter. Let's examine what happens in the position domain, also known as the spatial domain, and in the time domain for this example. What tasks are necessary? So first, in the position domain, there's our field of view, 24 centimeters. We assign it a coordinate system where 0 is in the middle of the x direction. On the far left, we have x equal to minus 12 centimeters. On the far right, we have x equal plus 12 centimeters. We know we have to apply a gradient across this direction in order to spatially encode the signal. We know we have to apply that gradient for a certain period of time while we receive the signal. We know that we have to sample that analog signal a certain period of number of times, in this example 256 times, to get 256 pixels through the analog to digital conversion process. So these are the questions. What gradient strength is needed? What gradient duration is needed? What frequencies will be in this signal? We know we have to collect 256 samples, so how fast must we sample the signal, and for how long do we have to sample the signal? Let's first look at gradient strength and gradient duration. In practice, the user does not directly specify the gradient strength or the gradient duration. The user specifies the field of view, the number of pixels, and the bandwidth. Then the MRI system calculates the required gradient strength, gradient duration, and sampling interval for those parameters. Let's look at this same example again with a 24 centimeter view and desiring 256 pixels in the x direction. So what gradient strength and duration would need to be applied to achieve this? At the bottom, we see a gradient applied on either side of the 0 position. And the question is, what gradient strength and duration is required? Recall this model that we had from the spin gymnastics lecture, that when we require 256 stripes across the image to get 256 pixel resolution, and we look at the system of rotating balls, recall that in this system, the frame of reference is with respect to the center ball. It doesn't rotate. But to get 256 lines across the image, we would have to have the spinning ball on the extreme left of the image rotate 128 times relative to the center ball, and the one on the extreme right rotate 128 times in the opposite direction to achieve that spatial resolution. Recall that the precessional frequency is equal to the gyromagnetic constant multiplied times the gradient strength with respect to the frame of reference, which is 0 in the middle. And the number of rotations is equal to the precessional frequency multiplied by the length of time for which the gradient is applied. So the number of rotations that any ball experiences is the gyromagnetic constant times the gradient duration times the gradient strength at the position of that ball. Let's look at the same example and assign a bandwidth of 32 kilohertz to the same field of view in the same number of pixels. Here's our field of view. Once again, we have x equals minus 12 on the left and x equals plus 12 on the right with 0 in the middle. And we're going to have a bandwidth of 32 kilohertz. That means at the extreme left of the image, the rotational frequency would be minus 16 kilohertz with respect to the frame of reference, which is at the 0 position. And at the extreme right of the image, the desired precessional frequency is 16 kilohertz with respect to the center. So what gradient do we have to apply to achieve that difference in frequencies across the image? Well, the gradient strength is calculated by the formula of bandwidth divided by field of view multiplied times a constant. That formula will be developed in a subsequent slide, but suffice it to take that as a given for the present moment, and that comes out to 3.17 millitesla per meter. So we apply the gradient at that strength, and then while that gradient is being applied, we get a signal back on the receiver coil for a certain duration. How long do we have to apply the gradient? Well, according to that Nyquist formula, the sampling interval is 1 over the bandwidth, which is 1 over 32,000, or 31.25 microseconds, and we have to sample 256 times. So the total sampling time is 31.25 microseconds times 256 samples, which equals 8 milliseconds. So we have to apply the gradient for 8 milliseconds at the gradient strength that was already shown. We store the 256 samples as one line in K-space. And then we ask the questions, as a check on the system, we ask the question, how many rotations will occur at each end of the field of view with respect to the center? Well, it's 16,000 rotations per second times 8 milliseconds. We would get 128 rotations in one direction on one side of the image and 128 rotations on the other side of the image. So the formula works. With respect to bandwidth, why bother with bandwidth? Why not always have the same bandwidth all the time? Well, there are several image features that are affected by receiver bandwidth. First, let's consider signal to noise. Most of the MRI signal is near the center frequency, but the distribution of noise in the MRI signal is fairly evenly distributed across the entire frequency spectrum. So most of the signal coming from the tissue is, again, centered around the middle, around the center frequency, but the noise is distributed relatively equally everywhere. So towards the edges, we get diminishing signal, but constant noise. So as we increase the receiver bandwidth, the amount of noise getting mixed in with the signal increases, but with little increase in the signal. In fact, with decreasing signal. Thus, increasing the bandwidth decreases the signal noise in the image. So the signal noise ratio decreases. And the generally accepted formula for signal noise ratio is that it is proportional to the square root of 1 over the bandwidth. Bandwidth goes up, signal noise goes down. But bandwidth also affects other factors in the image, including minimum echo time, chemical shift, and metal artifact. Let's look at the same example, but with a changed bandwidth. So we're going to change the bandwidth from 32 kilohertz to 16 kilohertz and work through the mathematics with a 16 kilohertz bandwidth. So here again, we have the head placed inside the scanner. Same field of view of 24 centimeters, same coordinate system, minus 12 at the left, plus 12 on the right-hand side of the image. And Now we have a bandwidth of 16 kilohertz, so the frequency at the left side of the image will be minus 8 kilohertz with respect to the center, and on the right side of the image, plus 8 kilohertz with respect to the center. What's the required gradient strength? We use the same formula of bandwidth over field of view times a constant, and we find that we only need half as strong a gradient. We apply this half as strong gradient across the body part, and we apply it for a certain length of time over which we receive the signal. How long do we have to apply this gradient? Well, recall that the sampling interval is 1 over the bandwidth, but the bandwidth now is only half as large, so the sampling interval is twice as long. It's 62 microseconds rather than 31 microseconds. We collect 256 samples. We collect these 256 samples at 62 microseconds per sample, so the total sampling time is 16 milliseconds, twice as long as with the previous example where the bandwidth was 32 kilohertz. So the required gradient duration in this case is 16 milliseconds, and we store those 256 samples as one line in K-space. Why bother with changing bandwidth? Why not just leave it the same all the time? Well, there are several factors that are affected by bandwidth, depending on whether you increase or decrease the bandwidth. Let's just look at what happens when you increase bandwidth. There are some undesirable effects. Most notably, since signal and noise is proportional to to the square root of 1 over the bandwidth, signal noise decreases as you increase bandwidth. However, there are several desirable effects of increasing the bandwidth. The minimal echo time decreases, the chemical shift effect decreases, and medical artifact decreases. So if you can control the bandwidth, you can control these various factors. And in fact, there is some control of the user over the bandwidth within certain limits. This brings us to the final few points of this lecture. And these are the sampling interval, which is called delta t, and K and delta K. And we're going to go over these points in the next few slides before we end. Let's examine the relationship between the sampling interval, delta t, the field of view, and the gradient strength. We're going to use the same animation that was used in the spin gymnastics lecture and earlier in this lecture, where we have an array of black and white balls as is shown in the bottom left of the slide. Before the gradient is turned on, the white parts of the balls face us uniformly across the field of view. We will see when the gradient is turned on, the spins precess in opposite directions relative to the center. The higher the magnetic field relative to the center, the faster the spins precess relative to the center. The signal is sampled every time an additional full cycle of spin distribution occurs across the field of view. So at the beginning, we have 0 cycles of spin distribution across the field of view. We turn the gradient on. Let's watch what happens as time elapses. The spins precess. A period of time evolves, the sampling interval. The signal is sampled after 1 full cycle of phase distribution occurs across the field of view. That signal being sampled goes through an analog to digital conversion process, and a point is registered in data space. We wait another period of time, delta t. After another period of time, the spins precess more, and when there are 2 full cycles of phase distribution across the field of view, the signal is sampled again, goes through another analog to digital conversion process, and the next point is registered in data space, which we would call kx equal to 2. And this keeps happening after each full cycle, incremental full cycle of phase distribution occurs across the field of view until all the data is required has been collected. Let's take a second look at the relationship between sampling interval, field of view, and gradient strength. This time adding some numbers to the same example. So the increments in phase distribution across the field of view for each sampling interval are designed to be equal to 2 pi radians difference from one edge of the field of view to the other edge of the field of view to avoid aliasing. So in this example, we have a field of view of 0.1 meters. We have a full cycle of phase distribution across this field of view after a certain period of time, which is shown here. So there's 2 pi radians difference. So how long does it take to create 2 pi radians distribution across the field of view? Let's just look at this in purely qualitative terms without any quantitation. Well, it should be intuitive that the higher the gradient strength, the faster the spins precess. And therefore, these 2 pi radians phase difference will accumulate faster. So as the gradient strength goes up, you have to sample faster. In other words, the sampling interval is proportional to 1 over the gradient strength. What happens if we change the field of view? If we look at the example as I have stopped the video after 2 pi radians change from one edge to the other edge across the larger field of view, you can see that if we looked only at the middle columns of the image, we have not yet achieved 2 pi radians of phase distribution. We'd have to wait longer to get that 2 pi radians phase distribution across the smaller field of view, which in this case we've made half as big as the original field of view. So in qualitative terms, you can see that the sampling interval is inversely proportional to the field of view. If you make the field of view bigger, you have to sample faster, assuming you keep the gradient the same. If you make the field of view smaller, you can sample you have to sample at longer periods of time, so delta t would be larger. If we put these two things together, gradient and field of view, we can see that the sampling interval delta t would be proportional to 1 over the gradient strength multiplied by the field of view. And if we want to quantitate this and remove the proportionality symbol, the constant that is used is 2 pi over the gyromagnetic ratio. So the sampling interval is set to be 2 pi over the gyromagnetic ratio times 1 over the gradient strength times the field of view. That sampling interval is the sampling interval that is required to avoid aliasing. This brings us to the last item of discussion in this lecture before we summarize everything. And that item is K-space, K, and delta K. K-space is a formalism used in math and physics. It has been widely used in MRI since the 1980s. K is the wave number. It indicates the number of waves or cycle per unit distance. Note, it's not per unit time, but number of cycles per unit distance. K is the reciprocal of the wavelength, and it's given by the expression K is 1 over the wavelength. Since wavelength is measured in units of distance, the units of K are 1 over distance. For example, 1 per meter or 1 per centimeter. And delta K is the difference between two adjacent points in K space. So delta K is equal to 1 over field of view, as we'll see in the next slide. So let's discuss in delta K before we summarize. So Here we have a field of view of 0.1 meters in the x direction, and we have one full cycle in phase distribution from the left-hand side of the image to the right-hand side of the image. So it's one full cycle per field of view. In this example, we have two full cycles of black-white variation over the field of view. If we subtract one from the other, one has two cycles per field of view, and the other is one cycle per field of view. So we can see delta K is 1 over the field of view. What is the relationship between sampling time and delta K? Well, we saw in 2 slides previously that the sampling interval is equal to a constant multiplied by 1 over the gradient strength times the field of view. In the previous slide, we saw that delta K is equal to 1 over the field of view. If we put these two things together, we see that the sampling interval is equal to a constant times delta K divided by the gradient strength. So if we look at this for a given gradient strength, delta T and delta K are matched. Every time you double the gradient strength at a given delta K, the sampling interval is halved. And this brings us to the formula that we used at the very beginning. How is the required gradient strength and gradient duration determined? We use the formulas that we've previously used. So the sampling interval is equal to a constant multiplied by 1 over the gradient strength times the field of view. And we know, according to the Nyquist theorem, that the sampling interval is 1 over the bandwidth. If we put these two things together, a direct substitution, we can see that 1 over the bandwidth is equal to a constant times 1 over the gradient strength times the field of view. And therefore, the gradient that's required by reorganizing that formula is equal to a constant times the bandwidth divided by the field of view. The higher the bandwidth, the higher the gradient strength is required. The larger the field of view, the lesser gradient is required, and vice versa. So that summarizes the several points we tried to make. It was more mathematical than in the original spin gymnastics lecture, but it provides some extra detail and quantitation to some points that were raised and resulted in recurring questions. Thank you for your attention.